All right, so hi everyone. Welcome back to this series of lectures on disordered systems and the statistical mechanics of those. So last time we continued our study of Hamilton-Jacobi equations, and we proved in particular something that will be very useful for us, which is a way to assert the uniqueness of solutions of these equations. So you remember that, okay, first we introduced the notion of viscosity solutions. And last time we saw that these solutions satisfy a comparison principle. And in particular, from this, we can infer that there is a unique solution to the equation. And it's particularly nice for us because in some sense, the free energy that we want to study, for finite n, it is almost a solution to the equation. And what we would like to say is that this almost solution is becoming very close to the solution of the limiting equation. And the uniqueness of solution statement says something of this sort, except not as quantitative, because it just says that if we have two solutions, then they coincide, instead of saying one which is almost a solution and one which is a solution, which must be close. Anyway, so this will be of relevance to us, and we have already seen that for the standard Curie-Weiss model, we can know that any limit point of this free energy must be a viscosity solution of a particular equation with a fixed initial condition. And since there is a unique such thing, then we have shown the convergence of the free energy of the standard Curie-Weiss model to the solution of this partial differential equation. Okay, so one thing which is still sort of puzzling in what we have done so far is that as of now, we have two ways to express this limit for energy. One is the one we derived from large deviations, which is a variational formula. And one is by saying this, by saying, oh, it is the solution of this partial differential equation, something. Okay, and the first thing I want to do today is connect these two descriptions. And so more precisely, we're going to derive variational formulas for solution of these Hamilton-Jacobi equations. Okay, so let me remind you of in the general setting, we think of looking at the viscosity solution to the following equation. So h is some fixed function, which we assume to be, let's say, locally Lipschitz, or it's not very crucial. You can imagine it's just a smooth function. And we can, this is on R plus cross RD, and the initial condition, which, okay, I write like this. Maybe I should just write f of 0, comma dot, but I like to write it like this so that we remember it's the time variable in the first slot, equal psi. Okay, so and we are going to assume throughout that psi is Lipschitz. And let's assume throughout that psi is a Lipschitz function. Okay, in our study of the Curie-Weiss model, or the models that will show up later, all of the functions we study are uniformly Lipschitz, so no problem. And yeah, when I say uniformly Lipschitz, I mean that as opposed to locally Lipschitz, that there is a Lipschitz constant which works for everywhere in space, not just locally. All right, so I'm going to propose two variational formulas under some assumption. And as someone pointed out in the chat already, The first one is called the Hopflux formula. So here is the statement. So first, let me recall to you this notation for the convex dual. So here I want to take the convex dual of the nonlinearity H. So H star of Q, Q is a vector in RD, is going to be, by definition, the sup over P of P dot Q, this is dot minus H of P. Okay, so the statement is, so if this nonlinearity H is convex, then the solution to the PDE can be represented in the following way. So we have f of tx equals the supremum over y of psi of y minus t h star of x minus y over t. Okay, this is a fairly well-known representation, and here the representation is relatively simple. In particular, because our nonlinearity H does not depend explicitly on X or T. No, it only depends on the gradient of the solution. But more generally, if you can write something similar, if H is convex as a function of the slot where you put the gradient, even if it depends also on T and X. And in this case, the problem looks like you're trying to find some optimal path between between X and some place at the origin of time, this Y point. So you're trying to find your path, and the cost, it depends on this, what H is doing locally along the formula. So in fact, if you like to think about first passage percolation, for instance, then then you can think of this first passage percolation problem as, in fact, an optimization of this sort, and then you can relate this to a Hamilton-Jacobi equation where the nonlinearity also depends on the position. Okay, so just as a side comment. So it's a very classical result, let's say. All right, so that's one representation I want to present today. That's not the only one. So let me state the second possible representation under a different assumption. So confusingly, the second statement is called the Hopf formula. Well, the first one is called the Hopflux formula. So this one is under the assumption that the initial condition is convex, but not necessarily the H. So if psi is convex, then we have the following representation. I'm going to write it like this: f of tx equals the supremum over p, and then the inf over y of psi of y plus p dot x minus y plus t h of p. Okay, so that's a second statement. I mean, I say okay, not as if is it obvious that is true, but is the statement clear? So these two theorems are very interesting because each of them gives us, under some assumptions, a variational representation for f. It's quite interesting to see. So I presented the Hopflux formula in the way it is usually written, but we can, instead of writing H star, I can write explicitly what is the definition of H star. So here, yeah, a question in the chat is, what are the assumptions on H? I'm just assuming that it's a local ellipsis function. And yeah, I think that's it. I forgot if, I think that's it. Okay, I'm hesitant now if maybe you need to assume. No, I think that's it. No, sorry, I think that's it. The useful assumption in this theorem is that psi is a uniform ellipsis. This I keep. I think this is enough to make the proof work. Okay. Yes, so I want to massage the Hopflux formula a little bit first. So now I'm making some comments about these results. Let's say remarks. Maybe I should say rewritten. So okay, it's this here, but I'm going to rewrite this as this is the soup over P of P dot x minus y over T minus H of P. Okay, and then it's multiplied by T, and then I'm going to insert this minus sign here inside the supremum, so it's going to become an infimum. Okay, so what I'm going to get is f of tx equals the sup over y, and then the inf over p of psi of y plus p dot x minus y plus t h of p. Okay, so it's interesting because it is the same functional which appears, so this is the Hopf formula. This is the Hopflux formula, so it's a different formula. But it is the same functional which appears. It's just these orderings are different. One is a sup over p inf over y. The other is sup over y inf over p. Yes. So what is this function doing? So another remark I want to do. So this function. So at some point we need to optimize over p, and therefore no, I want to optimize over y. Sorry. So at some point we optimize over y. So this will impose that when we differentiate this functional in y, the gradient should be 0, right? So if I compute the gradient, I get grad psi of y minus p. Okay, so this should be 0. So this tells me that at some point that realizes this sup inf, I have to have that p equals grad psi of y. So so the optimization over p imposes that p equals grad psi of y. Okay, and similarly in the Hopflux formula, like if I optimize over p, I will want that p is grad psi of y. And when p is grad psi of y, this function, and let's say we fix t equals 0, then this function is just the tangent function of the initial condition at y. Okay, so then so the mapping y, so no, sorry, x gives psi of y plus grad psi of y dot x minus y is the tangent of psi at y. And this tangent now, okay, it's as a function of x, its gradient is constant, you know, it's an affine function, and it's grad psi of y, sorry, which was p. And now, if we add this t variation, we see that it's clear that the derivative in t is h of p, and the gradient is p. So it's clear that this whole mapping here is solving the equation. Okay, so oops. Let me so the mapping okay, maybe I'm going to rewrite it. Okay, in red, let's say. So with the right choice of p, is the solution to the equation with initial condition being the tangent of the initial condition at y, with initial condition. Okay, so in some sense, you're doing some you're approximating your initial condition by a lot of affine functions, and you're propagating all of these. Like each affine function defines the solution to the equation for you, and then you're taking some sort of envelope in some rational sense of this family of functions of the partial differential equation. If you do partial t, I mean this function which I did not give it a name, but let's call it g. It will solve. It will solve dtg minus h of grad g equals 0. Okay, the function in pink. Yeah, by right choice, I mean with so it's not necessarily a minimizer, but I mean if you find yeah, so you know if you find a p that does this optimization, yeah, you will have p equals grad psi of y. Okay, this is a necessary condition for being an optimizer. Okay, so that's one way to interpret the statement, is that in some perhaps non-obvious sense, if we try to like replace the initial condition by this envelope of affine functions, then we can actually express the full solution using this family of approximations. You cannot really solve the Hamilton. So there's a question about, can we find these formulas using the characteristic curves of the equation? So you cannot really solve the equation at arbitrary times using the characteristics, or at least not if you do it naively. But for short times, you can do it, and then things will match. Okay. Let me think if I want to make another remark. Yeah, so okay, so now I'm going to make to take 1 more minute to make a remark, which is a little bit advanced, and it's perhaps more for the experts. So you know, if you find it confusing, just ignore it for a second. But here is a question I don't know how to answer, which I think will be very interesting, and I'm going to explain why later. So imagine you have no assumption, neither H is convex, nor the initial condition is convex. Nothing like this happens. Okay, so maybe, let me take a step back. In these two cases covered by these equations, it is always the case that you can compute the solution by evaluating this expression at a critical point of this same expression. And now here is my question. If there is no assumption on the convexity of psi or H, is this still true? Is this still the case that you can always express the solution to the equation by saying that you compute this quantity here at some critical point of this same quantity? Okay, so it will not be a characterization, but it's still a valid question to ask. And I find this question interesting because I believe that this is how physicists talk about the limit free energy in the spin glass case. So it's not a characterization because they do not say, or at least as far as I understand, they do not say how to pick the right critical point. And because they kind of pretend there's a unique critical point, which is not always the case. But yeah, so and I don't know how to answer this question, and I don't know if it's true. But maybe some knowledgeable people in PDs know that it's true. Yeah, so there's another question in the chat. So why does the optimization over P imposes that P equals grad psi of Y? Well, it's kind of clear for the Hopf formula. And for the Hopflux formula, because the P is what we do first. And for the other one, it's not as clear, but the argument is similar to this envelope theorem we discussed last time, that you can pass the derivative through the first optimization that you have done. So in fact, it's true in both cases. But yeah, it's clearer when you do the optimization over P first. All right, so that was a fancy comment. If you have not understood it, no problem. It was meant to be a little bit far-fetched. I mean, not that I designed this, but it's just, I think it's interesting for experts to know that I wonder about this. I really think it's an interesting research question. And maybe if there is a PD person who knows the answer to this question, I would be very interested. All right. So I'm not going to provide proofs of these statements because it's a bit long, and so the Hopflux formula is proved in the book of Evans, and the Hopf formula, which is a little bit less classical, is proved if you go along the steps of the problem set number 6. So I decomposed the problem of showing the Hopf formula into digestible bits, or at least I believe they are digestible. And if you go step by step, you will find the proof of the Hopf formula. However, I would like to do something perhaps a little bit less fundamental, but which when I first started to play with these formulas, I was a bit intrigued by the fact that, so let me go back to the following displays here. So I was intrigued by the following question. So we know this is true as soon as H is convex. H depends on P. Yeah, but I'm optimizing. So there's a question in the chat. This the fact that P is equal to grad psi of Y is what you get when you optimize over P first. Okay. No, sorry, I got it wrong. Yeah, it's when you optimize over Y. Yeah, no, I think I did say it right. When you optimize over Y, you get grad psi of Y. Okay, so yeah, sorry, I think I said it wrong, at least in some instances. So here you optimize over y first, and so it's clear that grad psi of y is equal to p. And here it's not as clear, but I claim it's also true. You know, that you find a y that, if you find a p and a y that realize this identity, then it will also be the case that grad psi of y must be p. Yeah, sorry, I confused myself, but yeah. In one of the two instances, it's clear, and in the other one, I claim it's true, but it's less obvious. Okay, sorry for this confusion. Are there other questions? Did I confuse myself some more times? Okay, so yeah, I want to address one question which I found intriguing and has a very cute answer. It is, yeah, so it is that the Hopflux formula says this is true whenever H is convex. So the Hopflux formula. The Hopf formula says this is true whenever psi is convex. And so if both psi and H are convex, then both formulas should be true. Okay, so far so good. And yeah, I was kind of surprised at first that this does not look like your standard minimax theorem, right? Because here we have sup over p inf over y, and I'm claiming that if H and psi are both convex, then I can interchange these two things, except that the inf becomes a sup and the sup becomes an inf. And I was like, haha, this is kind of curious. I want to understand why this is true. So I knew it was true because I could do this, you know, long-winded proofs through Hamilton-Jacobi equations. But surely, if this is true, there must be a simpler proof. So I want to provide you the simpler proof. It's kind of at least I find it cute. Oops. So so let's say when both. Oops, I don't want to do that. So yeah, so here I would like to provide a direct proof that when these two things happen, when H and psi are both convex, the two formulas are indeed identical. And it comes down to the following proposition or lemma, if you want. I'm going to take two convex functions. And I claim that we always have the following. So sup over x inf over y of f of x plus g of y minus x dot y. This is always equal to the sup over y inf over x of the same thing. Okay, so let me first verify that this is what we want. So it's not exactly of the form we had, but so okay, in this notation, the variables over which we do the optimizations are p and y. And so in the middle, we have this minus y dot p. And then there's this some extra p dot x, but we can decide that, you know, instead of thinking that the convex function is h of p, or maybe th of p, we can think it's th of p plus x dot p. And then you apply the lemma and you're done. Okay. So it suffices to prove this proposition to justify that the two formulas coincide when the two functions are convex. So here is the proof. So recall this the Fenchel-Moreau theorem. Oh yeah, I wanted to make another remark. So I'm going to also make a remark. F of x is equal to the dual of the dual. Oh yeah, sorry. Someone sent me a private message. I meant yeah, there are too many. So yeah, I said f and g and then phi and psi. Sorry, just like this. Okay. So the Differential theorem tells us that if I take a convex function, okay, I have to have that it's lower semi-continuous as well, but here the functions are defined. They are finite on all of RD, so they are lower semi-continuous. So it's always true that they are equal to their bidual. And so I'm just going to write that this is equal to the dual of the dual. So the dual of F star is like this. Okay, so I want that we remember that point. I'm going to use this to justify the proposition. So I start with the left-hand side. And let's say that when I do this inf over y of g of y minus x dot y, this is minus g star of x. So this is the same as super over x of f of x minus g star of x. Right? And now I'm using this Differential thing that I recorded at the beginning. So I'm going to rewrite f according to the Differential formula above. So it's sup over x, sup over y of x dot y minus f star of x minus f star, g star of y. Sorry. Minus f star of y minus g star of x. Right? Do you agree? Just want inner soup over y. That's right. Thanks a lot. It's a very short proof, but I'm still struggling to keep the indices right. Did I make any other mistake? Looks good. So I hope it's good. So if it looks good so far, then I'm happy because the proof is actually over. Because this expression is symmetric in f and g. So you know, I have argued that I can exchange f and g, and this is basically what I wanted to argue. So I'm going to finish the proof more step by step, but in fact here the proof is already over. So okay, so let me interchange the soups. And thankfully, someone pointed out that they're over different variables. And now when I do the soup over x, I recognize, so x dot y minus g star of x, this is g of y. So this is the soup over y of g of y minus f star of y. And now I rewrite f star of y according to its definition. So this is soup over y inf over x, g of y plus, I say g of y, but I write g of x. G of y plus f of x minus x dot y. That's the end of the proof. Okay. So yeah, my opinion is that the proof stops here actually. But, no, yeah. So when you do the soup over two things, you can safely exchange them regardless. Yeah, so I wanted to make a last comment about the Hopf formulas. Let me scroll back up. Sorry that I forgot to do it earlier. Yes, so maybe I'll do it down there. Okay. Maybe I'll only do it for the hop formula. Okay, there's a question in the chat which maybe will require me to think some more, so I'll postpone it. Yes, so let me write one more time the hop formula. Okay, so let's just proofs of the formulas. So this is C Evans, and for Hopf, oops, this is C problem set number 6. And so now if both are convex, thanks to this observation, you also have for problem set number 6, you also have a proof of Hopflux. So yeah, let me rewrite the Hop formula one more time. Yeah, so what I want to point out is that when you do this infimum over y, you see it's infimum of psi of y minus y dot p. And so this is talking about the dual of psi computed at p. So let me rewrite this. Oops. Equals sup over p. Maybe I'm going to t h of p plus p dot x minus psi star of y. Okay, and this should remind ourselves the formula we found using large deviations when we computed the free energy of the Curie-Weiss model. So you remember for the Curie-Weiss model, instead of this h, I was using the psi variable, I mean the psi of p. Okay, p I was writing m, so it was t psi of m plus hm, and h was x, and minus psi star of I, and I wrote y, but I meant p. I'm sorry, today I seem to be making lots of mistakes in the arguments. Okay, so this, I'm going to come back to this later, but this matches, this allows to bridge the limit for energy we found using large deviations. With the solution of the PD. So I'm going to come back to this in the next chapter, but just so that you see the connection, at least a little bit. Yeah, and the last comment I wanted to make is, in this formula, if you set t equals 0, oh yeah, and another thing I should say is, when we do this Curie-Weiss model, indeed, the functions we look at are convex. In particular, the initial condition is convex. So the assumptions for applying this Hop formula are valid. Yeah, and the last comment I want to do is, if you set t equals 0 in this formula, what you get is the supremum over p of p dot x minus psi star of p, which is the dual of psi star computed at x. And since psi is convex, this is psi of x. Okay, so I verified here that this formula indeed has the right initial condition. Okay. Does that make sense? Okay, so maybe it's a good time for a break. Let me see if I want to add some comments. Yes, I think that's what I wanted to say here. Yeah, so let's take 10 minutes of break. Sorry that I made a lot of mistakes in the notation so far. I'll try to improve in the second hour. Yeah, so there was a question in the chat. Thinking. So I don't know how to answer this question, the question about gradient flow. Yeah, the question of Guilherme is that I don't think you need any assumption for exchanging two supremums. Like when I write, maybe I could write like this. So when I write sup over x, sup over y of f of x and y, I mean this is really the same as writing the sup of f and x and y for x and y varying freely. Okay, it's my usual water break then. Okay, so there's another question about the min-max theorem has some connections with constraint optimization problems. I'm not sure. So I guess you mean this interchange of sup and inf where I guess, okay, I'm scrolling with my mouse. So I understand you mean this result or no? I'm not sure how to. I haven't seen this. I don't know. Yeah, I don't quite have much insight about this observation besides that it's there. I don't know if it's classical. I would be interested to hear if people have encountered this thing in other places. Like, yeah, of course, I don't claim originality, but I don't know of a context where it's naturally occurring. When you do, normal these sort of min-max things, they involve you just interchange, but the sup over x remains the sup over x, and the inf over y remains an inf over y. And this is the sort of thing you want to do when you study two-player games or these sort of things. But in this form, I don't have a clear interpretation. Maybe there's some, like, in particular, it depends quite a bit on the exact form of what we are. I'm really using this of the form a convex function plus another convex function minus this dot product between the arguments. So it's yeah, I don't have a good insight. Okay, so someone is asking if there's a sign mistake. I guess as compared with what is in Evan's book, I suppose. So I think in Evan's book he writes a plus in the equation here. I think in to be verified, but I think here he writes a plus. So then yeah, it will change things. Okay, so one way to verify that things make sense is precisely by this heuristic I said, which is that you want that this function is going to be a solution to your problem as a function of x as when you fix y. So, and I think this works. But if you change the sign in the equation, then you will want to write a formula with some sign being changed. I don't know if that makes sense. Maybe there is a sign mistake, but at least right now I still have the impression it's okay. Ah, it was in the other formula. No, I still have the impression it's okay, but yeah, the fact is that from large deviations, we kind of know that this is the right formula. So that's also another way to verify. I'm going to come back to this. So if this was not clear, don't worry. I'm going to come back to the connection with our results on large deviations. Yeah, and about the exercises, the problem sets number 4 and 5 are about playing with the notion of viscosity solutions. So I think problem set 4 is mostly about playing with the definition of the solution. And okay, maybe the last 2 exercises are a bit more difficult, but the first 3 I think are manageable. And the problem set number, so you still believe there's a sign error, but why do you believe so? Because if you don't tell me why, then okay. Let me see. Maybe I wrote x minus y and I should have written y minus x. Okay, that maybe. Let me see. Yes, you're right. Okay, so let me double check. Okay, now I understand why you thought. Yes. Yeah. So you're right. I made an error here. Yeah, it's just that to verify the sign, I kept looking at things which actually are correct. This is where the error was. Sorry about this. Yes, you're right. Thanks for checking this. Yes. Now things are fixed. Thanks a lot. So now it makes more sense, I hope. Yeah, and I was describing the problem set. So problem set number 5 is mostly about playing with the comparison principle. So if you want to do that. And problem set number 6 is to prove the Hopflux formula. So I told you there are lots of exercises. They are not meant to all be done. Okay, it's just I was inspired to write many, so I didn't stop myself. But I understand that it's not really possible to do all of them. Okay, so I kind of hinted at the fact that this should allow, this formula of Hopf should allow us to bridge together this limit for energy that we found from large deviations with the limit for energy that we found using Hamilton-Jacobi equations. And now I'm going to come back to this. And actually, I want to discuss not just the standard Curie-Weiss model, but the generalized versions as well. Okay, so far, we justified these conversions to the viscosity solution for the standard Curie-Weiss model. But I want to discuss what happens for the generalized model as well. And I've spoken a lot about this generalized Curie-Weiss model precisely because something very interesting is going to happen. Okay, so that's why it's a separate chapter. Okay, so let me turn to this. So I think it's chapter 4. And yeah, I wish I had thought about generalized query-based models before trying to think about more complicated models, because I would have learned a lot. But I suffered, but you don't have to suffer the same way. All right. So let me recall the framework. So I want to identify the limit free energy of these generalized query-based models using this Hamilton-Jacobi equation approach. And as we'll see, things look nice when we are not too careful, but then a difficulty emerges. So recall that we give ourselves a smooth function psi. And the sequence of probability measures. Pn, and we assume that that sigma is smaller than the norm of sigma is smaller than square root of n under Pn. Okay, so if you want, it's a generalized version of our sum over sigma between sigma being a vector of +1s and -1s. Okay, and we consider the free energy, which is of the following form. So Fn of T and H. So 1 over n log integral exponential of Tn psi of 1 over n sum of sigma I plus H sum of sigma I dPn of sigma. So you remember that the standard query-based model is obtained by choosing psi being the square function and Pn being this product of Bernoulli measures, the balance on +1, -1. Okay, and we assume that when we set t equals 0, this thing converges to something. Okay, so at any given point, so Fn of 0h, we assume that it converges to psi of h. And this assumption is valid, for instance, as soon as we assume that the measure Pn is a product of a fixed measure. As soon as Pn is of the form of P1 tensorized n times. Okay, but it's, yes, the sigmas are in R. And so, but you don't need to, so there are other measures for which Fn of 0, dot will converge. No, here it's just the L2 norm, like dPn of sigma almost surely, this is true. Okay, so think of it as, think of sigma as being a vector of IID coordinates, and each coordinate is bounded by one. You really lose basically nothing if you think that this is the case everywhere. Okay, so think of Pn as being of this form. It's the product of a fixed measure, and P1 is a measure whose support is in the interval -1, 1. That's all I want to say. Okay, just to not have to worry about boundedness issues. Okay, and let me continue with the notation. So I remind you that we write this angular bracket to denote the expectation with respect to the Gibbs measure associated with this energy. So you know that dot 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 is what I use to as replacement for this whole thing. This is dot dot dot. You mean the expectation is bounded? I think this is a consequence. Like when we look at the bracket of the mean magnetization, for instance, it is bounded as a consequence of this assumption. I'm not sure if this answers the question in the chat, but maybe. Let me know if this answers the question or not. Because this is the expectation with respect to the Gibbs measure, and I don't remember if we have done the derivation for the full general model or only for the standard Curie-Weiss, but in any case, it's exactly the same. We have seen that when we differentiate in H, what we get is the mean magnetization. So yeah, so I still don't know if the question in the chat is answered, but if by the question in the chat it was meant that this quantity, no, it's sigma I. This is sigma I is one of the coordinates. Okay, so this quantity is bounded by 1/n sum of sigma I squared, then square root outside. So this is bounded by 1. It's not an assumption; it's a consequence of the assumption. So we have this, and we differentiate in T. In this general model, it is this guy which will show up, right? It's this psi that will show up when we differentiate. So I will get, oops, we'll get psi of 1/n sum of sigma I. Okay, and you also remember that when we differentiate twice in H, what we get is n times the variance of this magnetization. Okay, so very similarly to how we reason for standard Curie-Weiss, we would like to say that so when we see this, it suggests that most of the time this variance is going to be small. In other words, this magnetization will have small fluctuations. And if it has small fluctuations, then this quantity here should be very close to psi of the average. Right? All we do is the fluctuation of this quantity. If I pretend there's no fluctuation, then they will be equal. Okay, so let me write this. So I'm going to be interested in the difference between dTFN and psi of dHFN. You remember we did that with the square function, and here we observe that this is the variance, and then we replace the variance by 1 over n second derivative, and we were happy, and then we spent quite some time discussing viscosity solutions. But now it's a little bit less transparent because there is this psi function in the middle. But still, yeah, we still have this idea that if the variance of 1 over n sum of sigma is small, then this term should be small. So yeah, maybe just to make sure, the comment I did before. So we already did this calculation, but let me. You always have this inequality, and this by assumption is bounded by 1. Okay, almost everywhere. And I'm going to want to use this. So I would like to say that I would like to relate this to the variance of the magnetization. I would like to say that this quantity underlined must be small if the variance is small. So this is going to be just some sort of little Taylor expansion of psi that allows me to say this. So I'm going to do this Taylor expansion now. So the function psi is smooth. So for every, let's say like this, x, y, between -1 and 1, I can approximate the psi function by its tangent at x. And when I do this, I make an error of quadratic size. Okay, because the psi function is smooth. And I'm going to use this with, sorry, I put the parentheses. I'm going to use this with y being the mean magnetization, like this 1 over n sum of sigma I, and x being the mean value of that quantity. Okay, so that this will be psi of the expectation. This will be psi of the true quantity, and then I'll take the expectation outside, and this should look like the variance. So let me do this calculation. So psi of 1 over n sum of sigma I minus, and here I use the average of the same guy. Oh, sorry, I made a mistake. Okay, maybe I have to compress this a little bit. Okay, that was too mistake. Okay, and now imagine I try to compute the expectation of what is inside the absolute value. And I bound it by the absolute value of the expectation. No, sorry. I compute the expected value of what is inside, and I insert the absolute value inside the expectation, and I apply this bound. So taking expectation, so when I take the expectation of what is inside the absolute value, this guy is subtracted by the mean, and this is a constant. So this term will disappear. Okay, and now I have the expectation of psi of the random variable minus psi of the mean value of that random variable bounded by the variance of that one variable. This is what I wanted to show. So yeah, if I want to do this derivation for any, so maybe you can assume, yeah, I want this thing to be valid for any value of h. So I'm not sure if it's really possible to assume that this min maximization is always 0, because you know this is under the Gibbs measure, right? Like so I have to. Yeah, if you want, yeah. So yeah, that's maybe the way someone put it in the chat is more appropriate. So instead of writing this inequality with absolute values, you can write it without the absolute values, and you write a double-sided inequality with minus c blah 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 on one side and plus c on the other side, and then you take the expectation. I think the way I was thinking of it is that you apply Jensen in some way, but that's a much cleaner way to argue. Thanks for this point. Okay, so let me summarize what we have done so far. So we had this observation here, and now I found the bound for the right-hand side. I can say it's small in the sense of this variance type. So conclusion. This thing is smaller than some constant times the variance. And this is C over N times the second derivative. Okay, so it looks like we are also we're again well set to argue as before that as n goes to infinity, this function fn will converge to something which solves the equation partial tf minus psi of partial hf equals 0. Okay, because we have this like 1 over n second derivative as the right-hand side. But there is a catch, and the catch is that when we made this rigorous, we used this notion of viscosity solutions, and this notion of viscosity solutions was really tailored to the fact that the error term was of the form a positive small terms times second derivative. We really used the fact that there was a sign here. Okay, so let me say the inequality. So again, as was pointed out in the chat, maybe it's best to just think of this as being two inequalities. And this one is nice and similar to what we have used before. Looks reasonable. Looks nice, let's say. But the converse inequality, which says that this is larger than minus C over N second derivative, looks scary because here we have minus a small term times the second derivative. Looks bad because we have a minus sign. Okay, so it's a little bit of a funny phenomenon of viscosity solutions, is that you have this guy, you have this term which goes to 0, but you have to worry about the sign of this term going to 0. Yeah, that's the way we build the solution. Okay, so this should really ring alarm bells. It feels like we are trying to do something backwards, and there will be problems in our arguments. So when the function psi is convex, this does not show up. So for instance, when psi is the square function, so if psi is convex, because this term we try to control, it is here. Oops. It is here. When psi is convex, by convexity, you know that this term is non-negative, the term inside the absolute value. Okay, so by convexity, we know that that this is always non-negative. Okay, and that's why when we did the standard Curie-Weiss model, we did not encounter any problem. Okay, I mean, for the standard Curie-Weiss model, there was an equal sign. That was even nicer. But we could reproduce the argument using the fact that here we have this nice inequality. So this one here and this one here. Okay, these two inequalities are sufficient for us to carry over the proof that we have seen for the standard Curie-Weiss model. So let me write this down as a precise statement. So recall it's under the assumption that Fn of 0h converges to psi of h for every h, and psi is convex. The function Fn converges to the unique viscosity solution to the equation partial t f, so let's say f partial t f minus psi of dhf equals 0 with the initial condition psi. Okay, and by the Hopflux formula, so recall that our function Fn is convex, so in particular psi is convex, so we can apply the Hopflux formula, and it tells you that f of t and x, so I'm going to write h for the second variable, just to stay consistent. This is the supremum over p, so I'm going to use m of t psi of m plus hm minus psi star of m. Okay, and if you remember, this is exactly the formula we got from large deviations, because psi star of m tells us this is the cost of making sure the magnetization is close to m. And once we have done this alignment, the function in the exponential looks like this: txi of m plus hm. So we recover the result from large deviations. And in fact, we extend it because here we have not assumed that psi is C1. Okay, and so here I'm not going to give the proof because it's really exactly the same as the one we did for Curie-Weiss. Okay, so for Curie-Weiss, I mean for the standard Curie-Weiss, we had this equality, but if you replace by this double-sided inequality with a 0 and a c over n second derivative, everything works nicely, no problem. Okay, and now what I want to discuss is what we do when psi is not convex. And I find this conversation very important because in particular, when we deal with spin glasses, basically, this is always what comes to you. Basically, any function you want to look at has the wrong convexity. Oops. Seem to have a connectivity issue with my... Let me see what's going on. Okay. Just a second. Sorry about this. It's a good time for questions. All right, Zoom is going to deal with non-convex functions now. We are not afraid. All right, so what happened? I'll figure out what happened later. Yeah, so now I want to discuss what happens when psi is not convex. And so maybe for a second you can think, oh, maybe we did not. Yeah, so I didn't. So for spin glasses there will be a xi function. If you want for the Sherrington for this SK model I discussed in the introduction, the relevant xi function will be minus the square function. So it's a very good question because it will exactly match what I'm going to say now. Yeah, maybe you think, oh, but we did these inequalities, but we were not careful enough. Maybe in truth, this negative sign does not really show up. But take for instance, psi of p equals minus p squared, which indeed I claim in relation with the chat, with the question in the chat, is very symptomatic of what we will see for spin glasses. So when you take psi of p equals minus p squared, what shows up? So let me scroll back up just to display this error term again. Yeah, so here it is, this thing on top of the page. So let's think that psi is minus the square function. So here we have, so this term is minus the second moment of the magnetization. And this is going to be plus the square of the first moment. So here it's exactly minus the variance. Okay, so when psi is is minus the square function, what we get is, so we get, it's an exact calculation like for standard Curie-Weiss, but what we get is the same with the wrong sign. And yeah, I mean, this should ring alarm bells, and perhaps I should not say it too loudly because then Zoom is going to crash again. But this is really something that should make us very worried that our proof strategy is not correct. Exactly. Yeah. So someone in the chat is pointing out that in this case, before you take the logarithm, when you define fn, when we define fn, we write 1 over n log of blah blah blah. If you look at this blah blah blah, this blah 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 is actually a solution of the backwards heat equation. And when you think about these things, you think it's crazy to solve the backwards heat equation, but in fact, this thing inside is an exact solution of the backwards heat equation. And then when you take the log, you get that expression. So let me say, this looks very alarming. Okay, and let me say one more time, it looks very alarming because the way we built viscosity solutions is precisely by leveraging on the fact that there was a plus sign here, not a minus sign. And the way out, the way we're going to still manage to save the day is by leveraging on the fact that the functions are convex. So we're going to rely on the following observation, which I owe to a discussion with Stefano Bianchini. I'm going to call it a theorem. I'm going to call it a convex selection principle. Also, I'm going to try to state it at some level of generality, like not just for this equation showing up for Curie Weiss. So I'm going to use again the language of this equation posed in RD with this nonlinearity H. So let's F be a convex function. So really, what will do a lot of the work is the convex function, such that, so I'm going to assume that the initial condition is C1, and the equation, and such that, and that solves, let me say it please. Oh, yes, and that solves. And okay, I'm struggling to express it as good as I can, and such that, let's see. The equation that we care about is satisfied on a dense set of points. Of our plus cross RD. Okay, so by this I mean you assume that there exists a set of points which is dense, such that at any of these points, the function is differentiable and it solves the equation. I mean, the relationship that is displayed is satisfied. Does it make sense? So these are the assumptions, and the conclusion is that then F must be the viscosity solution of the equation. I'm going to write A, but for a fixed initial condition, there's a unique viscosity solution. I mean the same equation. Does that make sense? So it's a bit of a twist in the story, if you want, because initially I told you it's not enough to satisfy the equation almost everywhere. Even we found examples of things which are Okay, so I see questions. So at the beginning, I said, oh, it's not possible to identify the true solution by just saying that the equation is satisfied on a set which is dense, and even if it's a set of full measure. But here it works. We managed to select the right solution by only verifying the equation on a dense set, provided that we assume that the function is convex and that the initial condition is C1. So there's the selection because there are lots of functions which satisfy the equation almost everywhere and which are not the viscosity solution. We managed to select the viscosity solution thanks to the fact that the function is convex. Okay, so I mean, it's just I want a handle on this theorem so that later when I call it, I can use a quick name that we all understand. If you have a better proposal, I'm also willing to hear them. But yes, that's a very good question also in the chat. The assumption of convexity is jointly in both variables. Okay, so yeah, if you have better proposals for the name, I'm willing to hear it. And the selection, yes, because or maybe identification principle could be also a name, because we identify the viscosity solution. That's right. So on a dense set is a very weak statement. In fact, it's not even a set of full measure. Like maybe it's true for. I mean, anyway, you can imagine dense sets which are very sparse. And using this result, we will manage to get out of the woods with our problem. So, are there questions on the statement? A dense subset of this cross problem. Yeah, for instance, all the rational points. Mm-hmm. The usual assumptions on H, like. Or maybe I should say that. Do I use this? We'll prove this next time. I forgot if I use that F is uniformly Lipschitz. So now I have a little doubt the solution. But so let's say that F is Lipschitz, just to be on the safe side. And in this case, we don't need. So H is also Lipschitz. We assume everywhere it's Lipschitz. So and H can be locally Lipschitz. That's fine. So for instance, if it's the square function, that's fine. And the little f, let's say that it's uniformly Lipschitz. Other questions? So next time, my plan is first to explain why, using this result, we can solve the generalized Curie-Weiss model, and then to prove this this statement. Okay, so yeah, so thanks for your attention, and I'm happy to take questions, but let's yeah. So let me. I'm going to go back to this step. So there's a question about. Yes, thanks for Lei Zhang, who explained the argument much better than I was doing. So when we take the expectation, the best way to think about this is. Okay, so let's say for a second I erase the absolute value, and now I take the expectation. Then we get one bound, right? This is clear. But now I want the second bound. So, but I had proved the inequality with the absolute values. So I can also write the inequality like this is also true with a minus. And so then I take the expectation again and I get the other bound. But yeah, also you can use Jensen as explained in the chat. But maybe this is a clearer way.